Okay, so moving on from this content, so this was where we were looking at a beam that with the forces acting on it looks like it's going to be moving, rotating around that fulcrum, and I had introduced you to the concept of moments. So moments are the instance where a force will create rotation rather than linear movement, right? So that 16 Newton force is going to try to make that beam rotate around the fulcrum. It generates a moment, and the idea behind this is that we're no longer just comparing the magnitude of forces, so you can see that 32 is bigger than that 16. We're comparing moments now, because the distance to the centre of rotation takes effect. So in terms of the forces, that 32 is twice as big as the 16. In terms of moments, because of the way the distances work, it's a lot larger than twice as big. It creates a much larger moment than the other because of the way the distance is, because the distance is much bigger as well. Yeah, so moments are like, you know, forces multiplied by distances. Okay, so in this one I've kind of sketched out the answer, so you end up with an answer that's 1000 Newton meters. That's the same as having 1000 newtons acting at 1 meter. That's the force and distance that would result in that moment. Yeah, so that's what we have. Okay, so these were the questions you were asked to do. I'm just going to quickly do one of these questions, right? So you were asked to work out the total moment. So you should have went clockwise, 17 times 5, and then this is anti-clockwise, so that's minus 34 times 10. So that equals 17 times 5 is 85, minus, I don't need that, so that would be 340, which is minus 255, and you need to put the units in. Obviously that would be Newton meters because it's a moment. Now that minus sign, all that minus sign tells us is that it's anti-clockwise. It's an anti-clockwise moment, you know, but we would have to round it to the correct number of significant figures, so you'd be totally okay writing 300 Newton meters anti-clockwise. You could write the word anti-clockwise if you wanted. So that's the type of activity that we were doing before, just to find out what the resultant moment is on a beam. Given a bunch of moments, what's the resultant moment? The trick in here was that the distance for that one is actually 8 meters. Remember, it's the distance to the fulcrum. Okay. So in this one, the bracket would have looked like, because they're both clockwise, it would have looked like 6 times 4 plus 6 times 8, and that would have given you your total moment. So it's that 24 plus 48, so that's 68, 69, 77, 72 Newton meters. Round it to the correct number of significant figures, 70 Newton meters, and then state whether it's clockwise or anti-clockwise. So that's clockwise. And then this one was, I'm not going to do this one because you get the picture. Okay, so that was working out the total moment on these beams. And here I've set up a new one, right? So, you know, we do this exactly the same way. What is the total moment on this beam? So the total moment is going to be the clockwise, so that's 20 times 4 minus 10 times 8, so that's 80 minus 80. The total moment on that beam is 0 Newton meters. It is not moving, it is balanced. Okay, this beam is in equilibrium. It is not moving. The clockwise moments and the anti-clockwise moments equal each other.
What's that?
So this is what the next set of questions are going to be about. The next set of questions are going to be about, can we calculate how to put a beam into equilibrium? Because that's the ideal. That's what a a structural engineer would spend time doing, is trying to make sure that a structure isn't moving. So the next set of questions look slightly different. The next set of questions look, I've obviously, this is my second attempt at this, so I've already got content in there. Right, so here we've got a beam set up where there's two forces on it. One's 8.4 metres away and the other's 12.4 metres away from the fulcrum. We know that one of them's 17 newtons, and then the question is, what do we want the other one to be in order for this beam to be in equilibrium? So this is calculating for equilibrium now. So we're going to do it slightly differently. We know that there's a condition for static equilibrium that says that the sum of the moments, let's say clockwise, must equal the sum of the moments anti-clockwise. We've already kind of talked about that. So the idea is that this moment, 17 times 8.4, must equal F1 times 12.4 in order for this thing to be balanced. So this is how we're going to lay these this maths work out. We're going to start off by stating our static equilibrium equation, our condition for static equilibrium, and then we're going to fill in the blanks. We're going to substitute in the correct values. So we're going to substitute in the values for the clockwise moment, which in this case is F1 multiplied by its distance to the fulcrum, 12.4. That must equal, now it does say sum, right, but there only is one. And then again it's the sum of, so this one's going to be 17 multiplied by 8.4. And then we can fill in the blanks here, so that works out, I think that's 142.2, isn't it? 17 multiplied by 8.4 equals 142.8. 142.8. F1 times 12.4 equals that. So I want to rearrange this equation for F1. There's different ways to talk about doing that. If a number is multiplying on one side, you can just delete it from there and it will show up as a divider on the other side. The other way to think about it is I'm just going to divide both sides by 12.4, knowing that that will cancel out, leaving F1 on its own on that side. But whatever I do to one side of the equation, I have to do to the other side of the equation. So I end up with divided by 12.4 on that side. So F1 equals 142.8 divided by 12.4, which equals divided by 12.4. 11.52. Let's round that and put the correct units in. So it's going to be two significant figures. So that's 12. It's a force that I've worked out, F1. So that means it's newtons. To two significant figures. So that's how we do this. So as long as that's 12 newtons there, then this beam is in equilibrium, because I laid the equation out like this. Same deal on this one. I'm going to do this one as well. There's more forces on here, so now the sum will, it will be a sum. We will have to add things together. What I'm going to do is I'm going to get lazy with that. I don't like writing it like that every time because it takes me too long, so I'm going to start doing that instead, right? But that's me just writing this. So we always start the same way. Sum of the clockwise equals the sum of the anti-clockwise. I expect to see you doing this whenever you do these questions. So let's work out our clockwise moments. So F1 is a force that will generate a clockwise moment. Make sure you take the distance to the fulcrum. It's a popular mistake. Some people go F1 times 2, but it's the distance from there to here that we care about. So that's actually F1 times 4 is our first clockwise moment. And then we add that to any other clockwise moments. The 6 newtons force will generate a clockwise, and its distance is 2, so that's 6 times 2. That's all of the clockwise moments. Let's find our anti-clockwise moments. 11 multiplied by its distance to the fulcrum is 4.
What's that?
And any other anti-clockwise moments? Yes, we'll put that 4 multiplied by 2. Okay, so let's solve some of these brackets. So we've got 4F1 plus 12 equals 44 plus 8. So 4F1 equals 52 minus 12. Yeah, we've just moved that 12 over the other side, it's adding 12 on that side, so it's subtracting 12 on that side. 4F1 equals 40. Move that 4 over, so divide both sides by 4, it disappears for this side and appears on this side as a divisor. So F1 equals 10, and it's already the correct number of significant figures. Just need to get the units right, so it's a force newtons. Now, in these diagrams, in both cases, it's a force that's missing, but equally, it could be a distance, and that shouldn't matter to you, because when you substitute all your numbers in, and if you look at this bracket, which is the moment that's generated by this force, it doesn't really matter at this point, once you've written it down, it doesn't matter what one's the force and what one's the distance. If you look at this one, alright, that says F for force, but it could equally say D, and that could be the force. It won't matter. It won't matter in the rest of your rearranging. It only comes to bear when you put your units in. So if you're working out a distance, you go through exactly the same process, but you'll end up putting in meters instead of newtons. So with that in mind, I've then got these 3 questions for you to do. So in this case, F1 in the first question, that is your only anti-clockwise, or that force is generating your only anti-clockwise moment. Over here, it's going to be part of a sum. F2 is going to be part of a sum of anti-clockwise moments. And in the third one, it's a distance that you're looking for, so be careful. Also, be careful with the way I've laid this out. Remember, when you're creating a moment, it's the force multiplied by its distance to the fulcrum, distance to the centre of rotation. So in the case of the 2 newtons, it's going to be 2 multiplied by 4. Be aware of that, watch out for it. Okay, go ahead and do those questions.